All right, let's dive right into this explainer and unpack the absolutely critical, literally life or death implications of the P0A0D fault in high voltage batteries. We're looking at the ultimate defense mechanism in electric vehicles today, that crucial fifth dimension of system high voltage execution and global safety. You know, when we talk about high voltage systems, we aren't just talking about a dead battery leaving you stranded on the side of the road. We are talking about active safety systems that have to react faster than the blink of an eye to prevent truly catastrophic failures. 50 milliseconds. That's it. That is the exact microscopic window the vehicle's brain has to recognize a physical break in the circuit, process the danger, and entirely shut down the high voltage power. If it fails to do this, you risk lethal electrocution or these massive high voltage arcs that can instantly lead to fires. It is without a doubt a zero margin for error scenario. So how exactly do we monitor something so fast? Enter the High Voltage Interlock Loop, or HVIL. You can really think of the HVIL as a microscopic high-speed digital tripwire. It intricately threads through all the key high-voltage components. We're talking the connectors, the manual service disconnect, the battery covers, the whole shebang. If any of these are physically compromised while the system is live, this tripwire snaps. It is the active defense core of modern EV safety. So here's our roadmap for today. We're going to hit 5 key areas. 1. Decoding the P0A0D fault. 2. Smart diagnostics and architecture. 3. DFMEA, designing for prevention. 4. PFMEA, perfecting the process. And finally, 5. DVPNR, extreme production verification. Kicking things off with Section 1, decoding the P0A0D fault. So, the P0A0D fault. That's the diagnostic code thrown when the system detects that our tripwire has been broken or it's experienced a severe impedance distortion. Now, there are basically 4 underlying ways, physical, mechanical, electrical, and electromagnetic, that this tripwire can fail. First up, human error. A technician might push a connector in, but, they fail to slide the secondary latch fully into its locked track, which causes a fake open circuit. Second is fretting. As the car vibrates over years and years of driving, microscopic movements wear down the metal pins, causing resistance to just spike wildly. Third, we have terminal pushout. This comes from bad crimping or harsh testing probes that actually destroy the internal springs. And finally, there's the invisible enemy, electromagnetic interference, or EMI. Modern 800-volt inverters create massive, high-frequency electrical noise that can literally drown out our tiny safety signal. Moving right along to Section 2, Smart Diagnostics and Architecture. Because of all that heavy EMI noise and the incredibly strict safety requirements we have, a simple copper wire, it just isn't smart enough anymore. To avoid false positives, modern EV systems totally abandon static DC signals. Why? Well, think about it. If a damaged GC wire shorts against the car's chassis, the system might read voltage present and think everything is completely fine, creating a massive, dangerous blind spot. Instead, they use dynamic pulse width modulation, or PWM, which is essentially a continuous square wave. The system is constantly checking for a very specific pulse pattern. You literally can't fake a perfect pulsed wave just by accidentally shorting a wire. If that specific pattern breaks, the system instantly knows there's a problem. Now, to process that pulsed signal, engineers use a brilliant dual-layer architecture. Layer 1 is a software debounce algorithm. This essentially gives the system a 150 millisecond grace period to filter out tiny microsecond misfires caused by, say, driving over a really rough pothole. But what if there's a real emergency, like a crash? That brings us to Layer 2. A hardware-level comparator circuit completely bypasses the main software processor. If it detects a crash flag or a manual disconnect, it ruthlessly cuts power to the main contactors in under 50 milliseconds. No questions asked. This dual-layer system builds an incredibly intelligent fail-safe response. The vehicle doesn't just panic and instantly shut off power under all conditions, because, frankly, losing all power at 70 miles per hour on a busy highway is a massive safety hazard in itself. So if you're parked and you turn the key on, it blocks startup entirely. But if you are actively moving and the fault trips, it derates available power to 50%, lighting up red warnings on your dash so you can safely pull over. Only once your speed finally hits 0 does it permanently lock the state machine down. Which brings us to Section 3, DFMEA, or Designing for Prevention. Because this fault directly threatens human life with the risk of electrocution and fire, it receives the absolute highest safety severity rating possible in design failure mode and effects analysis, a severity 9. This means the engineering budget and the physical protections dedicated to preventing it are just massive. To combat that Severity 9 rating, designers go all out with heavy physical armor. High-coverage shielding completely separates the wires from high-power magnetic interference. The connectors are waterproof to extreme IP68 and IP69K standards, and they feature secondary mechanical locks. But honestly, the most surprising detail here, breathable Gore valves. These are microscopic membranes right on the battery pack that let air pressure balance out, which totally prevents internal sweat or condensation that could cause electrochemical corrosion on our vital interlock pins. All right, on to Section 4, PFMEA, perfecting the process. Look, the best design in the world doesn't matter one bit if it's assembled poorly. So the industry relies on incredibly strict process controls to eliminate human error on the assembly line. When an operator plugs in a connector, it isn't enough to just push it in. The process literally requires an audible click sound from the secondary lock, which is then instantly verified by a camera system linked directly to the factory software. Shielding crimps are strictly tested for torque and pull force, and those tiny surface-mounted components processing our PWM signal, every single one of them undergoes 100% solder paste inspection and full 3D automated optical scanning. And right before that battery pack leaves the factory floor, it faces an intense end-of-line test. Every single pack must pass a rigid impedance scan, proving that the total dynamic resistance of the entire interlock circuit is safely under 1 ohm. If it's over 1 ohm, the factory system automatically halts the line, immediately flagging a hidden defect. And finally, Section 5, DVP&R, our extreme production verification. Before a design is ever approved for the road, these systems face massive abuse through design verification plan and report testing. They torture test these things. Engineers inject high-frequency, 1.5-volt electromagnetic noise directly into the system just to prove the software's 150 millisecond filter won't trigger a false alarm. Then they take the wiring harnesses and subject them to 300 hours of violent 3-axis shaking while swinging the temperature wildly from -40 to 85 degrees Celsius. This proves those physical pins won't suffer from that microscopic fretting wear we talked about earlier. Now, one of the absolute most clever physical tests they do is the break low, then high geometry check. Imagine a technician accidentally pulling a plug out while the system is completely live. The low-voltage interlock pin is physically designed to be shorter than the dangerous high-voltage pin. By testing this exact scenario with high-speed cameras and oscilloscopes, engineers verified that the short interlock pin breaks its connection exactly 100 milliseconds before the high-voltage pins even separate. This signals the hardware comparator, which violently kills the power 50 milliseconds later. So by the time those big, dangerous high-voltage pins actually separate from each other, the circuit is already completely dead. Zero power, zero chance of an arc. It's honestly an incredible symphony of physical design, software filtering, and rigid manufacturing all coming together. So to wrap up this explainer, I want to leave you with this provocative thought for your own engineering teams. If we can absolutely master this microsecond level defense for the physical connectors, how can we take these exact same lessons, the dynamic PWM signals, those ruthless hardware comparators, and apply them downstream to protect the rest of the vehicle's low voltage grid from high voltage surges during the pre-charge phase? It's a question that could very well define the next generation of EV safety. Thanks so much for joining me on this deep dive.